So start the recording. We're going to be solving this MCQ paper for the remaining problems that we have. Please shoot. বলো একটা করে বলা শুরু করো. I'll help you solve them. Anything from page number 2?
Sir, could you do number 3?
This one?
What's number 3?
Number 3. An airship is moving forwards at a constant height. So it's moving forward at a constant height. Which statement is correct? So if height is constant, it means vertical forces have to be balanced. Although the figure over here shows that one of the arrow is a bit larger than the other. Downward force is arrowhead is larger compared to the upper arrow. This can happen in questions. Figure might not be drawn to scale, but since it mentions it's at a constant height, which means these two forces should be balancing each other perfectly. So A is gravity has no longer has any effect. The airship now has zero mass. The potential energy is zero. The upward and downward forces are balanced. D is the obvious correct option, which brings us the situation of equilibrium of forces. বুঝছো? Did you ask for this number 3 or in the paper 2 number 3?
Sir, this one.
আচ্ছা, বুঝা গেছে কি? আচ্ছা. Anything else from this page? Okay, one thing that I would like to discuss for this one. The question says a person just supports a mass of 20 kg suspended from a rope. What is the resultant force acting on the mass? Now, what you should see that this question shows you there is a 20 kg mass and the person is supporting this thing. Just supports a mass means the person is pulling this rope strong enough just to hold this mass at its position. So the mass is considered to be stationary. There's the meaning of this word, just supports it, which would mean that there is no movement. So essentially there is resultant force 0. So the correct answer for this option is 0 Newton because it is just supported. It is not 200 Newton. The most common mistake to give is 200 Newton for the weight. Weight of the object is 200 Newton, which is working downwards, and the pull of the strings is working upwards by 200 Newton as well. Together they makes a 0 resultant force. All right. Anything from page number 3? Any question from this page? Anyone? Maybe not. We discussed this one earlier, as far as I remember. Page number 4. Five.
Sir, 37 and 42.
37 and 32.
42.
Achha, 37 দেখবো. Question number 37 says, what is the correct unit for the quantity shown? Okay. The reason this question is difficult for you because you haven't gone through a couple of quantities over here yet in your syllabus. But once you're done with your syllabus, this thing should be known to all of you. Electromotive force is basically a part of the electricity chapter, which has a effective unit of volts. This is not force. So all this name electromotive force, but it is not defined by force. It was named by some scientists who named it like that, but it is defined as joule per coulomb, or which is also the expression of volt. So this is not the correct unit. Latent heat energy is a type of heat that is responsible to cause objects to undergo state change. For example, if you have some ice at 0 degrees Celsius that is undergoing melting, where the melt water also is produced at 0 degrees Celsius, but the process have to absorb some heat from the surrounding or from other heat sources to make the process possible, which means that absorbed heat is responsible to cause state change from one form to another form while the temperature remains constant. This is what we call electromotive force. This is what we call latent heat, and the energy of latent heat is definitely joule. So perfectly joule. Pressure has a unit of Newton per meter square, not kg per meter cube. Kg per meter cube is the unit for density. এটা আমরা ডেনসিটি প্রেসার চ্যাপ্টারে কিছুদিন পর দেখব। আর ওয়েটের ইউনিট হচ্ছে, ওয়েট ইজ এ টাইপ অফ ফোর্স। দ্য গ্র্যাভিটেশনাল পুল অফ on an object is what we call the weight of that object. So weight is just a force. So ওয়েটের ইউনিট হচ্ছে নিউটন। সো এটাও ভুল দেওয়া আছে। অলটুগেদার এখানে কারেক্ট আনসার হচ্ছে বি। Uh, 42. Acha. 42 is a nice bit of question. I'll help you understand this thing. And I might also pick up the example for lift as well for this question when we are discussing this question. This is a nice one. Let's take it to the whiteboard. So let's have a look at this question, which is 42 number question in your worksheet, but in the actual question provided, this was number 5. So this question tells us that a hard stone hits the ground and comes to rest almost immediately. As the stone hits the ground, what is the direction and size of the force acting on the ground? Try to understand the content of this question. A hard stone hits the ground and comes to rest almost immediately. As the stone hits the ground, what is the direction and size of the force acting on the ground? Now, there are a couple of things you need to consider. So here is the ground. The stone will hit the ground and come to rest. Now, try to understand. If we consider the basic scenario, when a stone is only resting on the ground, the way Newton's third law works over here, that the object pushes W force on the ground downwards, and the ground pushes W force, reaction force of equal amount on the stone. So together, the resultant force is 0. Just for a stone to be on the surface. So if a certain ground has to make a object remain stationary on its surface, then the exact amount of force that has to be applied upwards is equal to weight. But that was not the case in the question. The question actually had the scenario that it was coming down from a certain height and it hit the ground and decelerated to 0. So currently the stone is on the floor, on the ground. It had some downward speed, and ultimately the final speed converted to 0, which means there had to be a significant upward acceleration to bring down this downward velocity to 0. Without applying an upward acceleration or deceleration, you cannot bring the downward velocity to become 0. So this ground is actually responsible to provide two forces. Actually, it provides force in as a single amount, but I'm having the idea of two forces to make sense with you, that this ground should apply the weight bearing force on the object. So one part of the upward force should be weight, and also there should be the force for deceleration, because the stone has to be brought to rest. So together, these two forces will be applied on the object whenever the stone actually hits the ground. This will bring the stone to rest, and this weight force will be responsible for the stone to stay on the ground. So the total amount of force that the ground should apply on the stone should be somewhat bigger than the weight itself. So if you might wonder that this discussion that I'm trying to give you right now is about how much force does the ground apply on the stone. The question didn't ask you that. The question asks you, what is the direction and size of the force acting on the ground? Now, that's where Newton's third law comes in. Stone can only get this force upwards whenever it is interacting with the ground with an equal amount of force downwards, which means stone is going to push the ground, and by Newton's third law, ground is going to push the stone upwards. So the stone pushes the ground. So ground experiences a force downwards. The magnitude of that force should be somewhat bigger than the weight of the stone, because that's what Newton's third law tells us, that every action has an equal and opposite direction. If the stone has to come to rest, it needs to experience a force bigger than W for the deceleration duration. And after the deceleration is done, that force reduces to W only when the stone is absolutely stationary on the ground. And for that to happen, for that duration of deceleration, the stone will also apply on the ground a force that is somewhat bigger than the W. এই আইডিয়াটা বুঝা গেছে কিনা?
If the ground applied force equal to weight, then it would not have stopped immediately.
Yeah, definitely, and that idea can be further entertained by one more thing, is that if I put it this way, let's say we have some loose material. Let's say we have some fluid, not necessarily water. Water actually provides a significant air. So let's say we have some carbon dioxide over here, CO2, not only air. So let's say you're gonna drop a stone into carbon dioxide. So what's gonna happen when the stone is gonna go through carbon dioxide? Let's say if the carbon dioxide provides exactly equal amount of weight on the object. So as the object falls through air, let's say it's speeding up. Let's say at the instant of coming through the carbon dioxide, let's say the speed of the stone is 10 meter per second. I'm just assuming this number. As the stone enters into the carbon dioxide amount within a container, let's say if the carbon dioxide applies an exact equal amount of force upward that is exactly equal to the weight of the stone, if the upward force is equal to weight, then this falling process would be an uniform motion of equilibrium force. So this would be a situation of terminal velocity. It means your downward force will be perfectly balanced by the upward force provided by the carbon dioxide gas, but as the stone goes down, it should be maintaining a perfect downward speed of 10 meter per second, because you haven't applied any force to actually decelerate it. You have applied a force to stop the acceleration, but you haven't applied any force to decelerate this, which means that velocity using which the stone fell into the carbon dioxide material, that should be maintained. But that was not the case over here. As per the question, the ground stopped the stone almost immediately, so that force has to be bigger than the weight. Make sense?
Yes.
Beautiful. One other thing that I would like to discuss in this part is for the example of weight and for the example of lift and weightlessness. This is another important topic which I did not discuss in the earlier part and which is very much related to this question, somewhat related to this question. Let me elaborate this concept. Did I talk to you about weightlessness yet? এই টপিকে আলাপ করছিলাম? I don't think so. Did I? No. Okay. Weightlessness is defined as the sensation of not feeling the weight. I'll say it again. Weightlessness is defined as the sensation of not feeling the weight. Here is how it works. Weight works on us. For example, I have weight because of my mass. Earth is pulling me down. How do I sense my weight? I sense the gravitational pull on my body that is caused by the Earth's gravitational force is not sensed by my nervous system anyhow. What I always sense, that I am always getting an upward force on the lower part of my body from some supporting structure. For example, let's say I'm sitting right now. So I'm experiencing an upward force from the chair through my hips and the lower thighs. So that section altogether is experiencing an upward force, which is perfectly equal to weight. And my skin in those parts are somewhat compressed. That sensation of compression is giving me the sense that I have weight. Important information. That sensation of compression gives me the idea of that I have weight. If I am standing on my feet, only on my feet, then my weight and then the reaction force is going to work through my feet, and that part of my feet would undergo some amount of compression, and that should give me the sensation of weight. If I'm lying on my back, all of my back part of my skin, which is in contact with the bed or the surface, would experience the upward force. So we sense our weight by experiencing the reaction force that we receive from the external body. We do not sense our weight, that is actually the pull downwards. First, appreciate this information. Our sensation of weight comes from sensing the reaction force, not the weight itself. That's how our nervous system works. The idea of weightlessness is that whenever our body does not experience that reaction force, that is what we call weightlessness. Weightlessness is not weightless. Any object that is within a gravitational field having mass will definitely experience a gravitational pull. If that gravitational object is Earth, we call that downward force. Gravitational force of the Earth is called weight. So if an object is within Earth's gravitational field, let's say on the surface of Earth, it will definitely have weight. But whether that weight is actually applied on a surface and a reaction force, subsequent reaction force is experienced or not, will define whether the person will experience the weight or not. এই পার্টটা কি বোঝা যাচ্ছে? Let me give you a little bit of example. Let's say our body, মনে করো, let's say my mass is conservatively 70 kg. Or should I go lower? No, 70 kg is good. I'm actually much higher than that, I think. I didn't measure last time. Anyway, so let's say my mass is 70 kg, which means my weight would be 700 Newton. I will experience my weight to be 700 Newton whenever I receive an amount of 700 Newton force upwards on my body from any surface. If at any point by some mechanism, if this upward force, for example, let's say this is me, figure not drawn to scale, this is me, and earth is pulling me down by 700 Newton, the ground is pushing me upwards by 700 Newton, so I'm experiencing the force over here, I experience my weight. If somehow this experienced force through my feet is less than 700 Newton, then I'm going to feel lighter. One of the very simple example of this is happens whenever we try to go for a swim. I'm gonna slowly expand the example so try to understand. Let's say here is a swimming pool, and this is the water level. I just jumped into the swimming pool. So what is happening? If I'm within the swimming pool, I shouldn't draw a stick man. Achha, let's say I'm gonna draw my torso with legs and hands. So let's say this is me. What happens whenever I'm within the water? I actually displace a certain amount of water, and that water, being a fluid, wants to get back to its original position by pushing me out. This process of developed force in the so that the inserted object can be pushed out of a fluid is what we call upthrust. Upthrust is a default force that any object experiences outwards of the fluid so that the fluid can come back to its original position. So if I'm in some water, my weight works downwards, that is 700 Newton. But because I am now in a much denser fluid, which is water, my upward force from the fluid might as well be, let's say, 200 Newton. So by default, I'm experiencing an upward force of 200 Newton, which means my body will now push down. These two forces are gonna partially cancel out each other. So the resultant force of my body working downwards is gonna be 500 Newton. My body will now push on the water molecules that is covered by my body by 500 Newton. So my body is gonna experience a upward force on my skin for all the parts that is submerged, an amount of force that is 500 Newton. That is somewhat significantly smaller compared to what I used to experience on when I was in dry land or within atmosphere. That's what gives me the sensation of light weight. That's what we call the sensation of partial weightlessness. Why is that happening? Because, I mean, you should consider that did the actual weight of myself become lower? No. What actually got lower? The reaction force that I'm receiving, that got lower. My body is experiencing a smaller amount of upward force. That's why I'm sensing my weight has reduced, but my actual weight is still very much the same, because our sensation of weight comes from the reaction force, not from the weight itself. The idea for lift is something like this. Let's consider this scenario. Let's say this is a lift box. This is the top floor. We're gonna go to the top floor later. Let's say currently I'm at the ground floor and I'm standing on the lift. The lift is currently stationary. Let's say my mass is once again 70 kg. So lift is perfectly stationary. This is the cable of the lift. So when the lift is stationary, I'm pushing 700 Newton on the base of the lift. The lift is pushing me upwards by 700 Newton. So I'm experiencing my weight to be perfectly 700 Newton. Let's say the lift is going to start and it's going to accelerate from 0 meter per second to let's say 5 meter per second is actually pretty fast. But let's say for the sake of discussion, let's say the lift is going to speed up to 0 meter to 5 meter per second within a duration of 2 seconds. So to achieve this, I need a bit of an upward acceleration. What will be that upward acceleration? 5 minus 0 divided by 2, that is 2.5 meter per second square acceleration. So when the lift is going to start moving upwards, it's going to accelerate for a small duration. And once it speeds up to the value that it wants to reach, then it's going to keep maintain that uniform velocity for a comfortable ride. It's gonna keep accelerating continuously because that's gonna put extreme pressure on our body, which is the high G cases, not going there. So within this 2-second time, I'm gonna have an acceleration of 2.5 meter per second square. In which direction? In upward direction. Now try to understand what is happening. I consider my body as an individual object. Try to understand this thing. One force that I have by default working on my body is downward 700 Newton. For this thing to happen over a duration of 2 seconds, I am going to require an acceleration of 2.5 meter per second square, which means my required resultant force would be F equals to ma, which would be given by 70 into 2.5. How much do you get from here? 175 Newton. So I'm going to require 175 Newton of resultant force in the upward direction. Now, where would this force come from? When the lift was stationary, my upward force was exactly 700 Newton. Let me draw that with green maybe. When the lift was stationary, my upward force was exactly 700 Newton. Available from where? From through my feet. For this 2 seconds, the lift is gonna push me upwards by that additional 175. I'm using the word additional, which means for that 2 seconds, my upward force on my body would be 700 Newton plus 175 Newton, which is about, let's say, 875 Newton. So when the lift is starting to accelerate upwards, my body should also accelerate upwards. So I need a force, resultant force in the upward direction. This force should be available on my body through the feet connection that I have at the base of the lift. So the lift should now push me at a force somewhat bigger than my weight. That force would be 875 Newton. That should work on my body for a duration of 2 seconds. For these 2 seconds, I'm going to experience an additional weight. My body will feel heavier because my skin, my feet are accustomed to receiving 700 Newton. Whenever I'm receiving more than 700 Newton, I will experience that weight. This is somewhat very much similar. I mean, why do I use the word heavier? I mean, why am I using the word heavier? Because the sensation of heavy stuff comes from this thing. For example, let's say if I was standing on fixed ground, I'm right over here, and I'm holding a heavy object on my head, which has a weight of itself of 175 Newton. If this is a scenario, if I'm holding an object of 175 Newton on my head, then I would be pushing down 875 Newton on the ground, my weight plus 175 Newton, and the ground should be giving me outwards 875. I would experience that pressure through my feet. And that sensation is going to tell me that I'm now holding a heavy object. That's what the sensation of heavier comes from. Do you understand my point? এই ডিসকাশনটা বুঝা গেছে কিনা? That we would require a bigger force, and that force has to come from the bottom of the lift, which should work on our body through our legs. Is this concept understandable?
Yes, sir.
So what happens beyond that point? So this will happen for the 2 seconds, and after the 2 seconds, the acceleration will no longer be there. So the lift would have reached this 5 meter per second speed, and the lift should now maintain uniform speed. So when the lift once again reaches to uniform speed, I will once again reach to 700 Newton. So when the lift is in motion, this upward force will once again become exactly 700 Newton, and uniform motion of 5 meter per second will continue. Uniform motion of 5 meter per second will continue. Let's say I now have reached to the desired level of the lift, and I'm about to slow down because I want to get out of the lift to the floor. So let's say when the lift is about to stop, it was now going upwards at a speed of 5 meter per second, which wants to come at rest. So it wants to become 0 meter per second. So to achieve this, there should be a downward acceleration, and that downward acceleration, let's say